In 1985, a young engineer named Gene Stroll stood before IBM's executive board with a wafer of gallium arsenide in his hand. It was darker than silicon, heavier, and according to every measurement, superior. Electrons moved through it 5 times faster. It generated less heat. It could work at frequencies silicon could only dream of. Stroll told the board this material would power the next generation of computers. They believed him. IBM invested hundreds of millions. Within a decade, gallium arsenide would be nearly forgotten, relegated to niche applications while silicon conquered the world. This is the story of why the better material lost. To understand why gallium arsenide failed, you have to understand what it was up against. By 1985, silicon wasn't just a material, it was an entire ecosystem. Decades of investment had built factories, trained engineers, refined processes, and created supply chains spanning continents. Every percentage point of improvement in silicon represented billions in R&D and infrastructure. Intel, Motorola, and Texas Instruments had bet their futures on silicon. They weren't about to abandon those bets for an unproven alternative, no matter how elegant the physics. The technical superiority of gallium arsenide was real. But it was competing against something more powerful than physics, momentum. The technical case for gallium arsenide was overwhelming. Its electron mobility was 5 times higher than silicon, meaning signals traveled faster and chips could operate at higher frequencies. It was more resistant to radiation, perfect for satellites and military applications. It generated less heat, solving one of computing's fundamental problems. It had a direct bandgap, making it ideal for optoelectronics chips that could emit and detect light. On paper, gallium arsenide should have been the obvious choice for the future of computing. But technology doesn't advance on paper. It advances in boardrooms, factories, and markets where physics is only one variable among many. The first cracks in the gallium arsenide dream were literal. The material was brittle and fragile in ways that silicon wasn't. In manufacturing, wafers would crack during processing. Yields were terrible. For every 10 gallium arsenide chips attempted, maybe 3 worked. Silicon fabs were hitting yields above 90%. Jim Turner, who managed a gallium arsenide line at Rockwell, remembers the frustration, spending millions on equipment only to watch wafers shatter during routine handling. The physics that made gallium arsenide fast also made it mechanically unstable. You could have the most elegant material in the world, but if you couldn't manufacture it reliably, it was worthless. Economics told the brutal truth. A 6-inch silicon wafer cost around $50 to produce by the late 1980s. A comparable gallium arsenide wafer cost $500. That 10-to-1 cost difference rippled through everything. Chips were more expensive. Computers were more expensive. Development was more expensive. Silicon's massive scale meant continuous cost reductions. Moore's law wasn't just about transistor density, it was about economic efficiency. Every doubling of production volume drove costs down. Gallium arsenide never achieved that scale, so it never achieved those economics. Companies choosing materials weren't just choosing physics. They were choosing business models. And silicon's business model was unbeatable. Despite the challenges, some engineers refused to give up. At companies like Vitesse Semiconductor and Triquint, teams pushed gallium arsenide forward with almost religious fervor. They believed the material's advantages were too great to ignore. They developed new manufacturing techniques, invested in specialized equipment, and attracted talent willing to work on the harder problem. For a moment in the early 1990s, it seemed like persistence might pay off. Gallium arsenide chips began appearing in high-end applications, satellite communications, military radar, fiber optic networks. These weren't consumer products, but they proved the technology could work. The believers had shown gallium arsenide wasn't a fantasy. But proving it could work wasn't the same as proving it could win. While gallium arsenide struggled with manufacturing, silicon didn't stand still. Intel and its competitors poured resources into improving silicon performance. They developed new doping techniques, shrunk transistor sizes, and invented clever architectures that squeezed more speed from the material. Every advance narrowed gallium arsenide's performance advantage. By the mid-1990s, silicon chips were operating at frequencies that had once seemed impossible. The gap was closing not because gallium arsenide got worse, but because silicon got relentlessly better. This is the paradox of technological competition. The market leader has resources to improve faster than the challenger can catch up. Gallium arsenide needed silicon to stay frozen in time. Instead, silicon evolved. Technology markets don't reward the best product in isolation. They reward the product with the best ecosystem. Silicon had something gallium arsenide could never replicate quickly enough: a global network of suppliers, designers, manufacturers, and customers all fluent in the same technology. Design tools were built for silicon. Engineers were trained on silicon. Quality standards were written around silicon. Switching to gallium arsenide meant rebuilding that entire network from scratch. The switching costs were staggering, not just financial, but cognitive, organizational, and social. This is how inferior technologies can persist, not through technical merit, but through the gravitational pull of established networks. Gallium arsenide was trying to create a new solar system while silicon's gravity held everything in orbit. Gallium arsenide didn't die, it found refuge in niches where its advantages mattered more than its costs. In your smartphone right now, there's probably a gallium arsenide chip in the power amplifier, boosting the radio signal. Satellite communications still rely on it. High-frequency radar uses it. These applications need speed and efficiency more than they need low cost. The material that was supposed to replace silicon everywhere ended up replacing it almost nowhere, surviving only where silicon's economics couldn't reach. This wasn't the future Gene Stroll promised IBM's board. But it was a future, and for the engineers who stayed with the technology, that mattered. Sometimes survival is its own kind of victory, even if it looks nothing like conquest. Behind the corporate decisions and market forces were people who bet their careers on gallium arsenide. Engineers who turned down safe positions at Intel to work on what they believed was the future. Executives who raised hundreds of millions from investors. Researchers who published papers defending the material against skeptics. When companies like Gigabit Logic and Gazelle Microcircuits folded in the late 1990s, those bets came due. Careers stalled. Retirement savings evaporated. Families relocated for jobs that no longer existed. The technology press wrote obituaries for the companies, but the real casualties were people who had believed technical superiority would be enough. They learned a hard lesson: in technology, being right about the physics doesn't guarantee being right about the future. There was another factor that rarely made the technical papers: gallium arsenide contains arsenic, a poison. Manufacturing it created environmental and safety challenges that silicon didn't have. Workers needed special training. Facilities needed expensive ventilation systems. Disposal of defective wafers required hazardous waste protocols. As environmental regulations tightened in the 1990s, these costs multiplied. Silicon was already cheaper, now it was also cleaner and safer. In public relations battles, gallium arsenide advocates found themselves defending a toxic material against an element literally named for sand. The optics were terrible. This wasn't why gallium arsenide lost, but it made the loss easier to accept. When something fails, it helps if you can tell yourself it wasn't worth saving anyway. Gallium arsenide's challenge pushed silicon to become better. Intel and other silicon manufacturers studied their competitors' advantages and systematically addressed them. They developed silicon germanium alloys that improved electron mobility. They created silicon-on-insulator designs that reduced power consumption. They invented new architectures that achieved high frequencies without changing the base material. The threat of displacement drove innovation more effectively than any research roadmap. By 2000, silicon chips were doing things that had seemed physically impossible 15 years earlier, not because the physics changed, but because engineers found creative solutions when faced with existential competition. Gallium arsenide lost the market, but it won something else: it made silicon better. That's a strange kind of legacy, but it's a real one. The gallium arsenide story teaches a lesson about how technology actually changes slowly, conservatively, and only when the economics align. We like to believe in disruption, in revolutionary technologies that sweep away the old order overnight. The reality is messy. Established technologies have advantages that go far beyond their technical specifications: economies of scale, trained workforces, compatible ecosystems, institutional knowledge, and simple familiarity. Overcoming those advantages requires more than better physics. It requires better economics, better timing, better compatibility, and often, better luck. Gallium arsenide had the physics. It didn't have the rest. That's not a story of failure, it's a story of how innovation actually works, with all its friction, complexity, and resistance to change. There's a parallel universe where gallium arsenide won. Maybe silicon hit a manufacturing ceiling in 1990. Maybe environmental regulations favored the material that used less energy, despite the arsenic. Maybe a different set of corporate leaders made different bets. In that universe, engineers trained on gallium arsenide processes. Design tools were built around its properties. Supply chains optimized for its chemistry. Silicon became the niche material, relegated to low-performance applications. The technology you're using to watch this video would be fundamentally different. This isn't fantasy, it's contingency. The path technology takes isn't predetermined by physics alone. It's shaped by decisions, investments, timing, and chance. We live in the silicon universe not because it was inevitable, but because it happened. Today, gallium arsenide thrives in places most people never see. Every GPS satellite uses it. The telecommunications backbone of the internet relies on it for optical transceivers. Military radar and electronic warfare systems depend on its high-frequency capabilities. The global gallium arsenide market is worth billions, not the trillions that silicon commands, but not nothing either. The engineers who stuck with the technology found meaningful work. The companies that survived became specialized and profitable. This wasn't the revolution promised in 1985, but it was a sustainable ecosystem built on real advantages for real applications. Perhaps that's a better outcome than winning and becoming the next monoculture, vulnerable to its own challenger. Gallium arsenide found its place by accepting it wasn't the only place. If you're working on something better, a better product, a better process, a better idea, the gallium arsenide story has a message for you. Being better isn't enough. You need to understand the ecosystem you're entering, the switching costs you're asking people to bear, and the advantages incumbents have beyond their technical specs. You need economics as elegant as your engineering. You need patience to find the niches where your advantages matter most. You need resilience to survive the valley between promise and profit. Sometimes you win big. Sometimes you win small. Sometimes you change the world by making the incumbent better. All three outcomes are victories if you measure them right. The engineers who believed in gallium arsenide weren't wrong, they were early, optimistic, and human. That's not failure. That's how progress happens. The material that could have changed every computer forever didn't change every computer. It changed some computers, transformed some industries, and taught everyone a lesson about how technology really evolves. Gallium arsenide reminded us that markets are human systems, shaped by more than physics and performance. They're shaped by timing, economics, networks, inertia, and the thousand small decisions that accumulate into destiny. The next time you hear about a revolutionary technology that will change everything, remember this story. Ask not just if it's better, but if the world is ready for better, and what better really costs. The answer might surprise you. Because in technology, as in life, the best solution isn't always the one that wins. It's the one that survives long enough to find where it belongs.